Good morning everyone. I am Vishnu Vigobi, Assistant Browser, MBC CET Pyramid. It's a topic from the analog integrated circuits, that is differentiator. In the differentiator, we will discuss about the ideal differentiator or basic differentiator. So what is the limitations of the ideal differentiator, and we are concluded with the practical differentiator and making the response of the ideal and the practical differentiator. So the name implies the differentiator is a circuit performs the mathematical operation of differentiation. Therefore, the output waveform is the derivative of the input waveform. The differentiator may be constructed from a basic inverting amplifier if an input resistor R1 is replaced by a capacitor C1, or interchanging the components resistor and the capacitor in the integrator, we will get the differentiator. So we can start from the basic. Diagram, that is the ideal differentiator. So we can start from the op-amp. There is a inverter configuration. So we will apply the positive input to the ground terminal. They are using a compensation resistor, that is R-com. So now we can interchange the components in the integrator. That is the RF, and the capacitor is in the input stage, that we will call C1. Then we will apply the input, that is VI. So the current component is IC, and there is a node is here, A and B. So the node voltage is VA and VB. So we can apply the supplies, and this one is the V out. So the compensation capacitor, resistor R-com is equal to the value of RF for the limiting of the input offset bias. So now we can make the analysis of the ideal differentiator. So the expression for the output voltage can be obtained from the node A, that is IC. We can write the current IF. Some of the current is coming to this input stage, that is IB. So we can write IB plus IF. We already know that IB is a very small value because of the op-amp have high input impedance. So we can write IC almost equal to IF. So IB equal to 0. So we can write the IC components. So IC is the capacitor. So basically C into d by dt of the voltage. But in the case of the capacitor, two terminals, one is VI and other one is VB. So we can write C1 d by dt of V is changed to VI minus VA. So that is equal to VA, that is IF VA minus V0 by RF. So apply the virtual ground concept. So whenever the VB is connecting to ground, so VB equal to 0, therefore VA equal to 0. So apply to this equation. So we will get the C1 d by dt of VI, that is equal to, what is the component? There is a VA is here, that is 0, minus V0 by RF. So now we can write the output equation of the differentiator, that is V out is equal to minus RF C1 into d Vi by dt. It's an important equation for the differentiator. So thus the output V out is equal to the RF into C1 times the negative instantaneous rate of change of the input voltage Vi with the time. Since the differentiator performs the reverse of the integrator function. Whenever cosine wave input will apply, cosine wave input will produce a sine wave output, and triangular input we will apply produce a square wave output, and vice versa happens. So I write the waveform. So there is a cosine wave I am applying, so we will get the sine wave. So we can write like this. So there is a pi values 2 pi, 3 pi. So what about the V out? So there is a, whenever the cosine waves are coming, so what about the output? Differential output is a sine wave, but there is a negative is here. So negative will going to be positive one. So we will get the output like this. The amplitudes are the same values. So this is pi, 2 pi and 3 pi. So now also perform the, what is the condition for, we are applying the spike waves or triangular waves. So the input like this and coming to like this. The amplitudes are same. So it's coming to like this. It's going to be like this, and it's going to be like this. So what happened? The output. So whenever there is a point is negative, so we can write like this. Okay, we will start like this. So we can write there is a negative point. This is a negative point. So negative point is here. So we will get the inverter condition 180 phase shift. So we will get the positive voltage. There is a positive voltage up to this. So positive is coming. It's going to be a negative one. So like this. There is a negative point. It's going to be positive, and like this happens. This is Vi and this one is V out. So no space is here, so I am writing in the one more line above. So in this topic we will discuss about the basic differentiator and how to make the output waveforms. So now we need to make the limitations of the differentiator. So we will write the limitation of ideal differentiator. So in the ideal differentiator has some practical problems. The gain of the circuit RF by XC1 increase with the increase in frequency. So we already know that XC1 is 1 by 2 pi. XC1 is equal to 1 by 2 pi of C1. So whenever the gain is increases with the what? Increasing the frequency, because 1 by XC1. So whenever the frequency is increasing, the gain is also increasing at a rate of 20 dB per decade. This makes the circuit unstable. Also the input impedance XC1 decreases with the increase in frequency. You'll know the equation like this. XC1 is equal to 1 by 2 pi FC1. This makes the circuit very susceptible to high frequency noise. when amplified, the noise can completely override the differential output signal. So there is a small levels of noise is coming in the output. The differentiator will make to differentiate the input, because there is any change, small variation in time, there is happening the number of minute differentiation. So we can predict the limitations of the ideal differentiator in the phasor equation, and we will conclude with the frequency response. So the phasor equation from the equation V out is equal to, from this equation V out is equal to, V out of S is equal to minus R of C1, the d by dt we can write S into Vi of S. So in the steady state, we can put S is equal to J omega. We will take the magnitude of the gain, A is equal to V out by Vi magnitude. So we can get the minus J omega Rf into C1. So the answer becomes omega Rf C1. Also we can write the gain equation. We will rewrite the gain equation by, say, general equation F by Fa, the frequency, input frequency, and a maximum or upper cutoff frequency Fa. So we can rewrite Fa is equal to omega Rf C1, that is equal to, we can cut this omega, we can replace 2 pi f, the F we are cut down, the Fa is equal to 1 by, we can write rewrite Fa is equal to 1 by 2 pi R of C1. The Fa is the upper cutoff frequency. So in the explanation of the practical op-amp, and we will conclude with the frequency response of the basic and the practical differentiator, that is the frequency response. So at a F is equal to Fa condition, the gain, F is equal to Fa condition, the gain A is equal to 1, therefore at 0 dB, and the gain increases at a rate of 20 dB per decay. Thus at a high frequency, the differentiator may become unstable and break into oscillations. There is one more problem in the basic differentiator. The input impedance W, the input impedance 1 by omega C1 decreases with the increase in the frequency, thereby making the circuit sensitive to high frequency noise. These limitations of the ideal differentiator are overcome using the practical differentiator with the additional components R1 connected in series with the capacitor C1, and one of the another component CF in parallel with the RF resistor. So after we are discussing about the practical differentiator, we will conclude with the frequency response simultaneously of the basic and the practical differentiator. So this is a practical differentiator. So in the practical differentiator, we already told you there is a resistor is in the ideal. You will apply a parallel one component, that is CF. So the other component, that is C1, is R1 is here. R1 series with the input capacitor C1. So we will apply the input. So this one is Z1. So we can write this one is a ZF. So in this we are applying the one of the component is R compensation. So that is equal to R1 parallel RF. So that is again equal to R1 because of the RF is very greater than R1 because it is a parallel one. Okay, we need to find the gain in the S domain because of we need to plot in the frequency response diagram. So we will start from the gain. So we out in the S domain condition. So V out of S by V in of S for the gain. There is a inverter configuration, so there is minus ZF of S divided by the condition Z1 of S. So we can write ZF of S is the parallel combination of RF and the CF. So we can write RF into 1 by S into CF plus RF plus 1 by S CF. So we can get RF divided by RF into CF S plus 1. So now Z1 of S input impedance, that is R1, is series with the capacitor SC1. So we will get the answer is R1 SC1 plus 1 divided by SC1. Therefore again V out of S by V in of S is equal to minus RF SC1 divided by RF CF S plus 1 into R1 SC1 plus 1. So we can rewrite this. So minus S RF C1 divided by 1 plus S RF CF into 1 plus S R1 C1. So make a assumption, that is RF CF is equal to R1 C1. RF CF is equal to R1 C1. So we can write V out of S divided by V in of S is equal to minus S RF C1 divided by 1 plus S R1 C1 the whole square. We will put the R C1 R1 C1 into this equation. We will get the answer. We will put this equation number A. Put this equation A. So we can also make the gain, that is in the frequency, input frequency divided by FB is another limiting frequency, that is FB. So we can make F by FB in the same step of finding the FA in the ideal differentiator. So F by FB omega R1 C1. So we can make F by FB, that is equal to 2 pi of R1 C1. Cut this. So FB is equal to 1 by 2 pi R1 C1. So FB is the gain limiting frequency. Also we can write F is equal to 1 by 2 pi R of CF. These are the same. So now we need to plot the frequency response of the ideal and practical differentiator. So frequency response, frequency response of ideal and practical differentiator. So there is the gain part. So this one is the frequency. So relative frequency in hertz. Relative frequency in hertz is the gain part. So starting from the minus 20, 0, 20, 40, 60, 80 and maximum point we can write 100. So there is a coming like this. So we'll start from the one of the terms need to be defining the frequency 10 squared f cube f 10 raised to 4 f and there is a 10 raised to 5 f. So we can plot this. So this is the first I am writing the open loop response. So whenever there is a input is applying, so there is a low frequency is coming. So what happens? The capacitor is in the open condition or blocking the input. So what happens? The gain is going to be very high. So we can write the linear diagram like this. So we can write the, already I told you now, there is f is equal to fa condition, that is in the 0 dB we can get the fa value. So we can write the, where is the fa is equal to the f value, the frequency f is equal to the frequency fa. What happens? The gain is going to be 0. So in the ideal is a open loop response. So whenever the frequency that is equal to fa, what happens? The gain become 0 or 0 dB, gain dB or 0 dB. So we are further increasing the ideal differentiator. What happens? The gain is going to be very high and the gain is increasing with the plus 20 dB per decay. It's going to be very increasing. So very increasing the gain, what happens? So the fluctuations and stability problems happens. The noise is amplified by the differentiator, or small minute variation in the signal differentiated by the very sensitive differentiator. So that will cause the stability and the response problems of the basic differentiator. So we will apply one of the frequency, that is the FB. So whenever the FB comes, so further increasing the frequency, what happen? There is up to a point FP, the value of the R1 and C1 or the RF and CF cases, the gain is going to be decreasing. So the gain is going to be decreasing in the further increasing the frequency. So this is the response of the closed loop response of basic differentiator in 20 dB per decay. So this is the another one, closed loop response of practical differentiator in minus 20 dB per decay. Why it is minus 20? It's going to be decreasing one, that is going to be minus 20 dB per decay. So in the ideal case, is increasing the 20 dB per decay is going to be stability and noise problem. But in the case of practical, we will apply the another two components, that is R1 and the CF. So we will, for the increasing the further increasing the frequency, is going to be decreasing the response by minus 20 dB per decay. And also that the gain is going to be a unity 1, in FC. That is the cutoff frequency. The cutoff frequency is the one of the frequency, that is upper cutoff frequency, that is FA, and FC is the unity gain bandwidth of open loop configuration. So from the last equation, the V out of S by Vn of S minus S R of C1 divided by 1 plus S R1 C1 the whole square. From this equation shows that the gain increases at minus 20 dB per decay for a frequency range less than that of FB, and decreases at a rate of minus 20 dB per decay for F is greater than FB. That is shown in the plot. So this 40 dB, 20 and 20, the 40 dB per decay variation in gain is due to the R1C1 and the RFCF factor. In ideal differentiator, the frequency response would have steadily increased at 20 dB per decay. This is a point, 20 dB per decay, even beyond feedback, which could cause stability problems at high frequency. The practical differentiator overcomes this noise variation by reducing the gain. So the value of FB is normally selected such that FA, FB and FC is the range. FC is here, FB is here, FA is here. So for effective differentiation, the T of the input signal is greater than or equal to RF into C1, where R1 C1 and RF CF is much less than RF C1. So the R combination connection is connecting to the non-inverting terminal to provide compensation for input bias current. Some of the application of the differentiator is wave shaping circuit, triangular to square wave generation, and the first differentiation of the differentiator we will use into a FM demodulation. So in this differentiator topic, we will start from the basic differentiator using op-amp. So the component is interchanged from the integrator, and we will make the circuit diagram and making the analysis. So in the analysis we will get the, whenever the frequency is increasing, the gain is increasing by 20 dB per decay. So if you are increasing the frequency in very large value, the stability and the noise problems happens in the basic differentiator. So we can change to a practical differentiator, or using the differentiator in the practical case, we will adding two components, one resistor value in the series to the input, and the one of the capacitor is parallel to the feedback element. So we will make an analysis in the S domain. So we will get an equation that is FA and FE value. So the FE value in the practical differentiator is 1 by 2 pi R1C1 or 1 by 2 pi RFCF. So in this case we will get the plot. So in the FA case, what happens when F is equal to FA case, the gain is going to be 0 dB. So further increasing the frequency, the gain is increasing by 20 dB per Tk. That is a problem. That is a problem in the basic or ideal differentiator. This overcomes by the practical differentiator. That is, we are applying the two components. So if you are further increasing the frequency, the gain is decreasing by minus 20 dB per Tk, and the fluctuations or variation in the basic differentiator is overcomes by the practical differentiator, and we will get the stable and stable and the practical differentiator, and also stability is achieved in the practical differentiator. So this is all about the differentiator topic in the Amp differentiator. Thank you everyone. This is Vishnu V. Gobi signing off. Jai Hind.